Okay, so on Friday we talked about the different transformation reactions, and we were able to go through a lot of them very quickly because it was all very analogous to what we talked about in steels, right? So the beta to beta plus alpha, right? We get the allotropomorphic grain boundary alpha that forms, right? And then we essentially have Widmanstätten, statin-like behavior, and the grain boundary alpha forms to a continuous layer, right? So that's very much like the growth of Widmanstätten ferrite from austenite. We talked about the Berger's orientation relationship and how this is how essentially you go from BCC to HCP. And unlike the orientation relationships in steel, this is always observed 100%, right? This doesn't deviate at all. So this is important to know, and it's just looking at how the two different variants that you can get from the 110, and that these laths that we see here are not perfectly straight, right? But we can grow by this same kind of ledge terrace type interface where this is our Berger's orientation relationship. This is a high angle, highly mobile interface, and we can grow the thickness of our lath by moving these ledges this way. All right, perfectly analogous to the growth of deformation twins, right? Right. And then we looked at the structures, and then we talked about the martensite, the different types of martensite that you can get, right? And remember, these are martensitic phases. So these are, you've got the alpha prime martensite, which is hexagonal, and then two orthorhombic phases. But remember, since these are martensite phases, there's no change in composition, right? So these will transform. They'll be at the same composition of the beta, and then we have to go through a tempering sequence where the different products will change to alpha, right? And then because that comes with partitioning of the beta stabilizers out of the alpha, will generally form some new beta in between the alpha, the newly formed alpha. Okay. We talked about omegaphase, right? And right, how this is a simple hexagonal structure, right? It's not easy to slip. It's going to cause brittleness in the structure, but it serves as a heterogeneous nucleation site for the alpha phase, so it has some advantages there. It can form either athermally or isothermally, right? And there's just been some really nice modeling work, actually, on omegaphase where they looked at the different slip systems potentially there, and the best estimates seem to be that omega titanium, the easiest slip system, has a critically resolved shear stress of significantly more than a gigapascal, right? So basically, these omega precipitates, all right, they act more like intermetallics or they're like purely elastic, right? You're not going to be able to cut. You're not going to be able to cut these, right, with dislocations, just because the energy to get them to slip is going to be so high. We looked a little bit about the reaction. I said, don't worry about it. And, sort of the morphology, and reiterated the point that these are easy sites for alpha precipitation, right? So the alpha can nucleate at the omega beta interface, right? So this is a area of research when that was really big at Ohio State. Professor Hamish Fraser, like, is the titanium guru, right? And before him, Jim Williams was here, right? Or not before him, but not too long ago, Jim Williams was here. It was also, he literally wrote, the handbook on titanium, right? So Lutering and Williams is, if you just look up titanium, just like a 2,000-page book called Titanium. And Professor Williams is one of the co-authors. And so this omegaphase reactions was like one of their favorite things to study. So when they taught this course, they had a non-ferrous metallurgy course as a quarter course for 4 semesters. And I swear half the course was the beta to omega phase transformation. I think they spent weeks covering all the tiny details of that process. Okay, so the reaction where we left off was this beta to beta 1, right? And so this is a phase separation in the beta phase. So what other alloys did we think of? What other system did we think about phase separation? Right? Essentially GP zones, right? This beta to beta 1 is analogous, very analogous to GP zones. So if you have a high concentration of beta stabilizers, you can get a separation into this beta 1 and beta phase. They'll both have the same BCC crystal structure, but different compositions and lattice parameters, right? And we get a very fine, forms very fine precipitates in the beta matrix, and this is going to happen on low temperature aging of the beta prime alloy. So what does this tell you? That the beta 1 or the beta prime solvus temperature is relatively low compared to the, right, in the beta field. So, right. And this is from some slides from Jim Williams. He has these, he's retired now, but before he came here, he was like the head of metal development for like GE Aviation, head of alloy development. He was here at Ohio State. He was like interim dean for a little while. And he retired from here, and he made millions of dollars teaching titanium short courses to industry, right? And these are some slides from his short courses, right? But basically, he makes the point that these are very similar to GP zones and aluminum alloys, right? They have a uniform distribution, which means how do you think these are going to nucleate? Homogeneously or heterogeneously? Homogeneous nucleation, right? So they're coherent with the different composition. The exact way that they nucleate is going to depend on the composition. If you have a lot of vanadium and zirconium, it appears to be like a more classical nucleation and growth. If you have molybdenum in there, you get a spinodal type decomposition because you end up with a miscibility a miscibility gap in your system. So it all depends on the exact composition, how this is going to form, right? And how stable they are and the critical size depends on the lattice misfit, right? And then you can imagine if you have, why would aluminum affect the stability? What's aluminum? Well, stacking fault energy with aluminum is always a good answer. But what's aluminum? Is it an alpha stabilizer or a beta stabilizer? Right? So think about that, right? Why would aluminum affect the stability, right? So this is essentially just the same information, but here we see precipitates along a prior beta oh, shoot, I'm getting ahead of myself. Right, I thought this was the next slide. I got things a little out of order. So we form the beta plus beta 1, and then we can nucleate, again, alpha heterogeneously at the beta on the beta 1, right? So we can get a very fine homogeneous dispersion of alpha, right? And we can nucleate the alpha at higher temperatures or lower undercoolings below the beta solvus when we have the beta prime phase. And yeah, what's that?
Second image.
This one. So this is the nucleation of alpha on beta 1, right? It's not, anytime you look at these TEM micrographs, if you showed me this and said this was titanium, I wouldn't be able to identify what this is just from looking at it, right? I'm not a microscopist. I don't, the resolution and the contrast on the old images is really bad, but they're nice to look at, so I throw them in here.
The lines.
This is a prior beta grain boundary, right? Right, and so, right. So this is grain boundary alpha that you have here, right? These bright spots are also alpha, but I would be really hard pressed to say that there was beta prime here, right, given the contrast in this image. Right. So here you can see it a little more clearly. This is a bright field TEM image. Here you see the beta prime particle with these laths of alpha nucleating, clearly nucleating off it. All right. So one of the key ideas here is this minimizes grain boundary alpha, right? Right. So grain boundary alpha can be bad for fracture properties, right? Because now you've got a connected path, right? So if we can get a beta prime field and then nucleate alpha heterogeneously from that, we can minimize the amount of grain boundary alpha that we have and improve properties. But this is going to require a very long aging time at low temperatures, right? So it's going to be very expensive to produce, right? And then the last bit is the alpha to alpha 2 ordering reaction, right? So if we have a excess of alpha stabilizers, we can form ordered phases, like the titanium 3 aluminum, titanium aluminide, right, which has a DO19 crystal structure, right? So it's still a hexagonal HCP-based structure, right? But we have clear aluminum sites and titanium sites, right? So we would have here a aluminum atom surrounded by 6 titanium atoms, right? And then every second nearest neighbor would be a aluminum, right? So remember, the difference going from a disordered to an ordered is in the disordered phase, each site has equal probability of either being titanium or aluminum, right? Of course, there's a lot more titaniums than aluminums, right? But each site has equal probability. In an ordered compound, there are clear sites, right? And the probabilities heavily favor one over the other, right? Okay. And then this just shows that essentially the slip systems in the titanium aluminide are going to be the same for both prismatic and basal, but the pyramidal, right, it's not going to slip this way, right? You're still going to have a 1-1-2 type slip direction. And so, but that's just the end of that. The next part is looking at some specific alloys and applications. And we will start it on this today and hopefully wrap it up on Monday. And then after Thanksgiving break, we will have get started with right into nickel. All right. Okay. So it's not visible? What's that? It wasn't visible on Carmen? Oh, I'm sorry. All right. Sorry, that's my fault. I meant for you to have this before. All right. So, but anyway, there's not a lot of sort of, I would say, notes, right? I mean, that you would be, right? This is just a repeat from before, just so you had the alpha stabilizers, the beta stabilizers handy, and just a recap of the things so they would be in front. The alloys are going to be classified into alpha alloys, near alpha alloys, alpha plus beta, beta alloys, and then we have advantages and disadvantages. I've taken a bunch of slides here. We'll get to them from Professor Williams's very expensive short course, so you guys get it for just as an inclusion to the regular what you would have for this class without spending several $1,000s, so having your boss spend extra several $1,000s of you to have it. I don't know if it's worth it, but there's interesting content there. You can tell that they're Professor Williams's slides because they're in Comic Sans, right? And so I don't want to be blamed for that monstrosity. Right? But he doesn't talk about alpha plus beta alloys. He just says alpha and beta, right? Like he just lumps the alpha plus beta alloys into beta. So that's one thing to sort of make make a note of. So we can break the alpha alloys down into fully alpha alloys, near alpha alloys, and these age hardenable alloys, such as titanium copper. Okay, so fully alpha alloys are going to be commercial purity, the most common being grade 2 alloys, titanium oxygen alloys. So where's the oxygen sitting? Interstitially, right? So these are interstitially strengthened alloys, right? Remember, the oxygen's going to get in the way of C plus A slip. It's also going to prevent deformation twinning. And then this aluminum 2.5 tin. This is listed everywhere, but I've never seen this alloy used for anything. Right? It's like listed if you look in like books or review articles on titanium. It's listed as an important alpha alloy, but I have no idea what it's actually used for. But right. So all right, these still go through the beta transits at high temperature, right? So we can get equiaxed alpha. We have a little bit of alloying elements. We can get martensitic alpha prime or the Widmanstätten Lath-like alpha, right? And this is all just going to depend on the cooling rates from beta, right? So these are really, really low tensile strength, very good ductility, right? And really good in creep, right? Relatively speaking, right? So they have good. They do much better than alloys with a lot of beta in them at creep, but they have generally poor formability. So they're really good at low strain rates, but not so good at high strain rates, right? So slow and hot, these alloys do really well. Fast and cold, they do really poorly, right? So why would they do poorly in formability? Right? It's just it's going to be the temperature dependence of slip, right? Accommodating C-axis deformation. So if you deform these things fast and at relatively low temperatures, you're going to form a lot of twins or have to activate very difficult C plus A slip. Right? Okay, so if we have small amounts of beta stabilizers, we enter the range of near alpha alloys, right? So less than 2% by weight. Right? A couple different compositions, right? Aluminum, zirconium, and tin. These act as solid solution strengthening. The molybdenum in these is a small amount of beta stabilizers. Silicon gives you some strength and creep resistance, right? Because this is going to segregate completely to the alpha, but then segregate to dislocations and impede mobility, right? So silicon will want to align itself on the dislocation cores, right? And so if we look at these compositions, what's really the difference here, right? So the biggest difference is an increase in the tin content and a reduction in aluminum, right? And so the tin's a better solid solution strengthener than aluminum at higher temperature. And we're not going to promote ordering with higher tin compositions, right? So just a little bit on sort of alloy design, right? Having a little bit of beta in there gives us some better formability, right? Increased response to heat treatment and annealing, right? We're going to lose a little bit of creep properties, right? And then all of these are sort of the alpha plus beta processed, right? What was the alpha plus beta processing that we talked about, right? So that's where you take it above the transits, cool down, go up into the two-phase region, deform, high in the two-phase alpha plus beta region, cool down, and then give it a small stabilization heat treatment. Everyone's like, it's incredibly hot in here. I see everyone's dozing off with the heat, right? I'm not sure what's worse, 4 o'clock to 5 o'clock. The 8 a.m. people came with like in their pajamas with like cereal, right? Right, and you can tell like everyone's groggy because it's not awake. Right here, everyone's groggy because it's the end of the day and this room is sweltering. So I don't take it personally if I see people, if I see eyes closing and heads bobbing. Right, no. Right, unless you start snoring, then I might get a little offended. But, right. So I mentioned these age hardenable alloys, right? So copper is a eutectoid beta stabilizer, right? And so you can, right? So it's going to be 2.1% solubility at the eutectoid temperature, but as you cool down, it reduces, right? So you've got a regime where you can do cold deformation in the soft state and then go up to temperature, right? So you can dissolve copper in, quench it in, cold deform it while it's soft, bring it up, and precipitate out copper, right? Pretty much, very much like processing aluminum alloys, right? So you get a precipitation of titanium to copper fine scale precipitates, right? These are, of course, metastable, just like the metastable phases in aluminum, right? These, like the other alpha alloys, are also very weldable, right? Okay, so the alpha plus beta alloys are what we usually think about when we think of structural titanium alloys, right? This includes Ti6-4, which is what the one alloy everyone knows, right? Also, if you just go by the ASME designation, this is called grade 5, titanium grade 5, right? I'm not sure how those got named, but typically people talk about using either grade 2 titanium or grade 5. Grade 2 titanium is commercial purity alpha. Grade 5 is Ti6-4, right? In the alpha plus beta process state, typically, right? So we're going to have for the suite of alpha beta alloys, roughly about 4 to 6% beta stabilizers, and then some added alpha stabilizers back in, which give solid solution strengthening to the alpha phase, and then stabilize it so that we don't dissolve it away. Right? We want to keep the alpha there at for high service temperatures. Right? We don't want alpha to dissolve while we're using it. Right? Ti6-4 is by far the most important. Right? And so this is properties of 6-4 in the alpha plus beta processed versus the beta process state. Right, and they're pretty comparable. The biggest difference being, right, the alpha plus beta processed. Right, remember the alpha plus beta, the deformation. We've got formation of equiaxed alpha grains in there. right? Where the beta process, we only have this colony or basket weave type structures. Right. So if you think about what I can ask you in titanium, right, a lot of it's going to result to this processing, alpha plus beta versus beta processing. And I'll show examples of that here, right? But if you look at the properties, right, we can see that you've got more ductility when we have these equiaxed alpha grains, right? But we have a lower fracture toughness and a reduced fatigue life. Right? Why would that be? Right? The ductility makes sense, right? You got nice grains, right? Without all these little laths and complex phases, so that makes sense. But why would the beta process grains, a colony or basket weave structure, be better? Give you better toughness. Right? It's just all about the crack path. Right? You've got this complicated microstructure, which means you're going to have a very tortuous crack path through your system. Right? Okay. So where are these used? This is again Jim Williams. Atomic sands. There's like an age, like people who are now like 70. Somehow, when PowerPoint came on, right? Because there's a lot of emeritus professors who, like, if you watch them give talks, they always use Comic Sans because I think it makes them feel happy or something. It's a formal font. It's lighthearted. But there's like an age. People who are now like 70, right? They all love Comic Sans font. But if you look at a high bypass ratio turbofan, right? So is everyone kind of familiar with the design of a jet engine? Right? So what's the difference between this high bypass ratio versus an older kind of jet engine design? Right? Where's most of your thrust coming from in a modern high bypass ratio engine? Is it the accelerated gases out the back, right, in a traditional jet? Or is it something else? You can probably guess that it's something else, otherwise I wouldn't be asking this question. All right, but what's producing most of the thrust? It's actually this big first stage fan blade out front. Right, this acts just like a big propeller, just much more efficient than a regular, right? Just an enclosed ducted propeller, basically. Right? And most of your air goes around the outside here as bleed air, right? And that's what generates your thrust. Right? And only a small part of the air actually gets ducted through the turbine itself. Right? And this fan, this first stage fan, actually isn't physically connected to the rest of this turbine, right? It's just an aerodynamic coupling, right? And the fact that you pull air through this, right? So it's the air being drawn through the center of these that causes this fan to spin and pushes the air around the outside. It's not a direct shaft coupling to the rest of the engine, right? But if we look at where titanium is used, it's used in a whole lot of places, right? So everywhere essentially except the hot stage turbine, right? Where you've got compression, you've got high temperature combustion going on, right? Where this is the nickel superalloy land in here. But everywhere else that's metal is a lot of titanium, right? This is kind of an older picture, right? What are these blades made out of? These are polymer matrix composites, right? And so a lot of the engine, essentially, that's you can break it down into high temperature components are nickel, medium temperature components are going to be titanium, low temperature components are polymer matrix composites, right? And that's a pretty good distribution of material that's in here. So here's just an example of the fan disc, right, that holds those big blades. This is titanium. I put this on here because a GE90, so this is, I guarantee you, everyone has flown on an airplane with this engine in it, right? If you've gotten on any modern aircraft where you see the little G spiral at the front of the, right? It's probably a GE90, right? And this is a Ti 17 is the alloy, but notice this, right? The raw forging weight before machining is 2,200 pounds, right? The actual part that flies is 370 pounds, right? So that means we're throwing away 5 times more material than we're actually using in the final part, right? So people like to talk about this, these buy-to-fly ratios is really important for industry, right? And we'll talk about why we need such large forgings for this in a little bit. Right? People are doing pretty cool stuff with reducing that, part of it by different joining techniques, right? So inertia welding was a big breakthrough, right? So solid state welding technologies like inertia welding was pretty big. And so inertia welding essentially just hold one piece still and you push the other piece next to it and spin it really fast. And then you get them both really hot by frictional forces, and you get plastic flow that squeezes all the interfacial gunk out, and then you stop it really fast and you have a solid state joint that forms. But you don't ever get it hot enough to melt, right? So you don't have any melt defects in there. And so a lot of really cool joining technology goes in there. There's also a lot of cast material that's in there, and really intricate casting geometry, right? Okay. So, as I mentioned, really a separation between nickel, titanium, and composites. It used to be that in older engines, titanium was all this space, right? But as composites got better, you can get composites like polyamide composites that can go to higher temperatures, right? The lighter weight, higher stiffness of these composites really took over. Okay, and then just kind of as a comparison, and we'll talk about this a lot with superalloys, but why superalloys are used for the hot section is really this, right? You can have higher initial yield strengths in titanium alloys, but they lose their strength with temperature much more rapidly, whereas superalloys have this anomalous strength behavior where they keep their strength out to much higher temperatures, right? And why that happens is a major section for discussion in the coming stuff. Right, so just properties of different things, just for your reference. Right? And then fatigue, crack growth, and different alloys. That's probably one I meant to take out. And then creep. I threw this in here just because it mentions this Larsen-Miller parameter, right? And if anyone ever looks up creep properties of metal, they'll talk about this. You'll see this mentioned a lot. So I thought it was a good to throw in just so you have the nomenclature of it. The actual data on the slide I don't care so much about. But has anyone's doing creep research? Has anyone ever heard of this Larsen-Miller parameter? Did Professor Anderson talk about it in mechanical behavior? Just a little bit, right? Basically, the idea is that this is just kind of a way of looking at large amounts, long time creep data, right? And so if you look at the time to rupture, right? So if you look at the time to rupture for a given stress, and then a constant times the temperature, this ends up being a constant, right, for a given stress, right? So if I have a given hold stress, I can look at the time to rupture at various different temperatures, and this relationship all comes out to be a constant. So it's a way of, if I have creep data at one temperature, to figure out what my service life is going to be for other temperatures given the same stress. So what people typically do is then calculate the Larsen-Miller parameter as a function of stress, right? And then essentially you have everything you need, right? If you know what the constant is, right, you can then look up the Larsen-Miller parameter and for a given temperature get your time to rupture service life, right? Again, it's not important for the exam. I don't care so much about these properties for this, right? I just wanted to, it's such an important sort of industrial design criteria. I just wanted to sort of throw everyone, have everyone see it again. Right? Okay. So fatigue, right? This is kind of, I think, a really beautiful example, right, of the effect of processing on property life, right? And this is what we were talking about before with tortuosity of path, right? So, right, very good fatigue life, marginal, and then very poor fatigue life, right? And I'm not giving any details on how these were processed, but this is the same alloy, probably 517 would be my guess, but I don't know for certain. But really, it's going to be the beta recrystallization, the beta grain size, the amount of continuous grain boundary alpha, right? So if you have these large prior beta grains with a well-developed colony or basket weave structure, you're going to be much better than if you have finer prior beta grains, because this prior grain boundary network becomes a short circuit path. And if you have, of course, these large right, these large grains with a just a perfect continuous film, you're going to be in the worst case. Okay, melting will just, you know what, I will just hit this real fast, and this will be the last thing. You can add a 1 here, right, because these slides are a little old. But so there's been a couple big processing changes in titanium. One of them has been this electron beam hearth melting, and the other has been advances in forging. We'll talk for the forging stuff after the midterm, right? But this electron beam hearth melting, that they basically have fine chips coming through. You've got electron beam that comes in and it flows through, and then you have an ingot that's then withdrawn and solidification here. All right, and this is the kind of the state of the art of melt processing for titanium. Then this ingot will then be forged, right? Because we have a solidification microstructure that needs to be broken down to form a regular polycrystal. And then this is just, of course, different melting defects that you can get. Okay, and I guess we have a couple minutes so we can look at the forging. So here we see this is a good last digit exercise, right? So if you look at these two optical images, right, and I said one of these behaves these two, the billets, the material that these came from, behave very different in something called dwell fatigue, right? So dwell fatigue means you load it up and hold it, right, before you release your stress, rather than just cyclic fatigue, constant sinusoidal. One of these does really, really well in dwell fatigue. One of them does really, really poorly. Would anyone have a guess as to which is which? Yeah.
I would guess one of the smaller grain sizes would have better dwell fatigue, harder for smaller grains.
So this one up here? Yeah, that's what everyone thought, right? Except it turned out to not be the case, but it actually ends up not being anything to do with the grain size. So that is make a guess.
I thought it would be close to that. But it'd be better if the smaller one has the grain boundary. So we have more better units.
Okay. So this was a huge problem. It still is a problem in titanium, but forging processes have been changed, right? And no one had an answer for this really until EBSD was invented, right? And if you put the EBSD images of these side by side, you see something quite drastically different about this, right? So if you look at this scale bar, this is half a millimeter. So this is 500 microns. So these are not individual grains, but these are big clusters of grains that have nearly the same orientation, which means I've got a whole bunch of small angle grain boundaries in here, right? And so essentially this acts like one gigantic large grain, right? And so if you now have a hard orientation next to a soft orientation, you have a stress concentration and a cracked path that can just essentially grow unimpeded across the big thing. And if you think about what the critical crack size is, right? The critical crack size in a part is going to be less than the size of one of these big microtextures, right? So this was all due to improper forging of these ingots. But of course, no one really knew that, right? They went through, gave them large amount of deformation, but it just was not nearly enough to break up these big microtexture regions, right? And so essentially, new forging processes essentially can essentially eliminate it, but you have to put in a lot more strain, right? Many more knockdown steps, right? You take a big square, squish it down to a skinny rectangle, turn it on its side, smash it, rotate it, smash it. You have to do a lot more of these breakdown steps than people ever thought before, right? And this is the really interesting part, because people did regular fatigue, and they're like, okay, we broke down our ingot enough, our fatigue life is good. But if you actually do this dwell, where you hold it at stress for 2 minutes and then release it, then go back up, hold it for 2 minutes, there was a huge debit. And this caused several very high-profile military aircraft failures, right? When you had rotors, right, like that one that we showed at the front that was holding all the compressor rotors, suddenly turned into shrapnel mid-flight because no one understood this dwell fatigue, right? So basically, the 1990s and early 2000s, this was the big issue with titanium. And everyone, the graduate students, you also saw Adam Pilczek's talk, right? He specifically didn't talk about this, but Adam did a lot of the original work to really clearly identify this macro techniques as the cause of this dwell fatigue issue, right? So he was Jim Williams' last student here at Ohio State, co-advised by Professor Dennis Fraser, is now has been at the Air Force Research Lab for quite a long time. He was just our distinguished alumnus award for this award winner for this year. But this is really Adam's claim to fame. Okay,